We have a rearranged session this morning. Andy from yesterday is going to continue on and talk about gene replacement therapy for Pompe. Then Nina Raben from the NIH wants to address us, and she hasn't got her PowerPoint projection presentation, but she's got some interesting things to tell us, again about Pompe. And I'll follow Nina with some information about new diagnostic tests for Pompe. And then Kevin O'Donnell will finish up the session talking about the International Pompe Association and movement. And I guess it sounds fairly short after yesterday's rather marathon-like presentations with lots of data. So I hope you've got a bit of space left after some sleep to take on some more. I wonder if Andy could start us off with gene replacement therapy. Please.
Morning. It's me again. I hope you didn't have too much of me yesterday. What I want to do now is I'm going to complicate your lives a little more. As I told you at Duke, we're looking at enzyme therapy replacement for Pompe disease. But when I started there it's almost 5 years now, my interest is in gene delivery. I've sort of always wanted to be a doctor, but I've always been fascinated by DNA and molecular biology, and I always thought, wouldn't it be great to be able to treat individuals with DNA and all these fancy techniques? And I think Dr. Chen, when he brought me on at Duke, realized what my interest was, but he knew in hindsight that it would be so applicable to Pompe disease. And I want to show you how. Okay, so Pompe disease is a genetic disorder. You have a mutation in your coding information, your blueprint for life, and that results in a mistake, an error that causes the protein that's supposed to be encoded by that information to be missing or not functioning. We went through this in nauseating detail yesterday. Okay? So we heard about how to replace the protein as a means to treat the condition. And now I want to move on and say, well, let's just go and either replace the information that's missing or just bring in the information that's missing. Actually, correcting the information would be the ultimate, right? To go into every cell in your body and just reverse the mutation that's there that's causing this. The people are looking at this. It's feasible, but it's a little farther off than what I'm going to talk about today. What I'm talking about is just bring in the information that's missing. And then in the hopes of now making the protein by the cell itself. Now, gene therapy, there's all kinds of ways you can describe gene therapy. I just want to give you a little overview of where the field is right now in general, because this is not, in my view, some sort of pie in the sky, oh, this is decades away. Right now, there's about 500 different clinical protocols testing various gene therapy applications in humans. Okay? So we heard that there's maybe 1 or 2 protocols for enzyme therapy for Pompe. There are 500 in place right now in humans. In fact, about 6,000 patients have received various forms of gene therapy. All of it's phase 1, which means it's all safety stuff. No one's looking to see if it works or not. That's the design of the trial. That's why the big criticism has been gene therapy has never worked. It's because it's never been tested in the right trial. It's all safety studies right now. I can tell you that if you look at the different types of diseases, cancer patients are the ones that are getting most of the gene therapy. And I think you can understand why. It's because many of them have failed every other option. The chemo hasn't worked. They've tried every trial. This is the last option for them, and this is the patient group that this is being tested in. Okay? There's ethical concerns with that, but that's the way it's shaping up. And in fact, there's all kinds of ways to deliver DNA into humans. I mean, everybody's got a little trick, a little angle. You could just inject naked DNA into people, and people are doing this in clinical trials. Viruses a cold virus. Someone sneezes on you, you catch a cold. That virus is delivering DNA into your body. And that virus has had several million years to figure out how to do that. Viruses are being used in a lot of trials. And in fact, if you look at this big yellow chunk here, this is adenovirus. This is one of the viruses, and this is the one I'm going to be focusing on. You can see there's 136 clinical trials using this virus in humans right now, okay? Of which at least 3,000 people have been injected with this virus, okay? Of which at least 600 have been injected directly in the vein with high doses of the virus. This is what it looks like under the electron microscope. It's very small, very tiny, compact little vector is what we call it. This is sort of a cartoon of how it looks. It's got this soccer ball kind of appearance with these spikes that stick out of it. And within this soccer ball is neatly compacted up the virus's DNA. Right? That's the information for the virus to turn one copy of itself into thousands of copies of itself once it enters a cell. And this is what it does. It comes upon a cell, as you get sneezed on, your son or daughter sneezes on you, you inhale the virus, it goes in, it happens upon a cell in your body, it attaches, and it rapidly enters the cell, disassembles itself, and delivers its DNA into the nucleus where the information can then be expressed by the cell. It can do this in about 15 minutes once it hits a cell. It's had millions of years to figure out how to do this and do it efficiently. And really, my work has been focused on, well, I don't have a million years to figure out how to get DNA into cell efficiently. Let's use what the virus has learned to do and take advantage of it for our own sort of desires. Okay? And so what we've done is we want to make a virus that can deliver the information for the enzyme that's missing in Pompe disease. Okay? So remember, we call that GAA. So we've engineered these viruses to now to have the information to make this protein. I'm not going to tell you how, because it's complicated, but we can do it. Now, remember yesterday I showed you this is what we're doing in the clinical trials with the enzyme, right? We take the protein that we get from Genzyme or Farming or hopefully Novozyme or wherever, and we inject it in, and the bloodstream delivers that to all the muscle cells, where the muscle cell receptors grab hold of that enzyme and drag it into the lysosome, right? That's the current enzyme therapy. Well, I say, why let these companies make the enzyme? Why not let every patient make their own enzyme? Okay? So this is the way I want to do it. Is you actually inject a virus that encodes the information to make that enzyme into the vein. Okay? And the way this virus works, it likes to go to liver tissues. Okay? So what we want to do is deliver the gene into the liver. Let the liver start making the enzyme for the body. And in fact, remember this, I showed you this yesterday, that the liver, we would hope, would secrete the enzyme. So now instead of injecting it, we've got the liver secreting it into the blood. And we let the blood then do the work of delivering it to all the muscle cells in the body. And then the muscle cell receptors, just like what they do with the enzyme, and I know it works with the enzyme, grabs hold of it and drags into the lysosome. Okay? So this is what's beautiful about this. And again, it's another advantage of, and I know it sounds crazy, of having Pompe disease versus some other muscle disease, is that I don't have to take this virus and put it into every muscle cell to get the effect. You see, imagine your body is 40% muscle, your mass. To do that, to inject this virus into every cell, every muscle cell, is impossible. Okay? And that's what, well, it's difficult. It's not impossible, it's difficult. But the liver is accessible very easily. It's just because the virus likes to go to liver. It's just a natural biology. And we can harness the capacity of this to become an actually enzyme factory inside your body to produce the enzyme and supply all the muscles in your body at once. So we made this virus. And in fact, when I was here in San Antonio last, I think it was 98 or 97, I had built the virus, but I didn't know how it would work. And I kind of nonchalantly, over coffee and stuff, asked some of the other scientists, what do you think? Do you think there'll be enough secretion, if we do this? And some people said it was an open question, because we thought massive amounts of protein would be required to correct all the muscle cells in the body. It turns out that this virus, once it targets liver, can make a lot of this enzyme. This is one of the few experiments I've actually done that worked the first time we did it. We took mice that were generated by Nina Raben that have Pompe disease. And let me show you an example. Here's a normal mouse heart, and it's stained with that PAS stain. You remember that stain that turns glycogen pink? Well, here's the normal heart. Here's one of the untreated knockout mice. You can see all the pink staining in here. This is abnormal. We injected the virus, and we look 2 weeks later at this animal. And about 4 days later, you can see it's a little less pink. But by 12 days, that animal was completely depleted of its glycogen in its heart. And we measured this too. The staining, the slide is a pretty picture, but we actually can measure the glycogen levels, and it's down to normal levels. In fact, every muscle in that mouse's body, the gastrocnemius, the quadriceps, the diaphragm, it's like a before and after, before and after, before and after. The glycogen dropped in all the muscles simultaneously with a single injection of the virus, and the virus did go into the liver. Yesterday during my talk, you could sort of see that I'm sort of focused on antibodies and their role and how they clear the enzyme and maybe prevent it from working as good in some patients than in others. One of the reasons I'm kind of angled that way is because I see what happens in the animals. These animals have never seen this enzyme. It's a human enzyme, so they react to it as foreign. So here's an example of looking in the blood of these animals to see how good that liver is producing the enzyme. Just for example, this white lane is just a knockout mouse, a Pompe mouse. There's no enzyme in there, obviously, because it has the disease. Even normal mice, they just don't make enough enzyme to secrete it. When we inject that virus, we see incredible amounts of the protein in the liver. Remember, this is just a single sample out of the mouse, 1 second out of its life that we took and look at it. That liver is constantly kicking it out, 24 hours a day, out until about 10 days out. And then we see this. At 18 days out, there's nothing in the blood. So it's there, and then it's gone. And there was 2 reasons for that, and most people would think it's that the virus has somehow been eliminated by the body. But we proved, and we published this, that we've made improved versions of this virus to kind of make it stealthy. It can go in and deliver genes and not trigger an immune response to the virus, per se. And we looked 6 months later, and that virus was still in the liver, okay? And we've done this by a number of molecular tests that I don't want to go into. And we've also we've made several versions of the virus to look if we forced the liver to secrete this protein in different molecular ways, what would happen. And we see the same sort of pattern. At 3 days, lots of enzyme in the blood, but at 17 days, it goes away. 3 days, 17 days. 3 days, 10 days, 17 days, sort of fading out. But all the time we look, the virus is still in the liver, even 6 months later. So what's going on? Why is this happening? And it turns out that when we look at the antibodies to this enzyme, they are peaking right at the time when the enzyme is fading out of the blood. You see? So the mouse takes about a week to 10 days to figure out that there's a foreign protein being secreted and makes an antibody that grabs hold of it. Okay. And what does that do in our little scheme here? Well, while the liver is busily making enzyme and secreting it into the bloodstream, eventually the mouse produces an antibody that blocks this enzyme from having access to all the muscle cells. Okay, so this is a problem. The interesting thing about this, though, is when we looked at these animals, even though we only had 10 days of secretion of this protein, and then the antibody came in and sort of fouled things up, we looked at the glycogen levels in these tissues, and they stayed down for at least several months. And in fact, even out 180 days, the glycogen level in the heart was still significantly less than even younger animals. And so we had a prolonged effect, even though the enzyme was not actively being secreted by the liver. It turned out that when we looked long-term, the glycogen levels stayed down for a while. And it turned out that the activity level in these animals, once the enzyme got into the muscle, it hung around for a long period of time. It turns out that this enzyme is very stable once it gets into the cell in this model. So there's another advantage of Pompe disease. This enzyme, once it goes in, it likes to hang around. In fact, here's a Western blot of liver tissues and heart muscle and quadriceps muscles from these animals. Just look at these lanes that say knockout and look right in this area, for example, in the heart. See, the knockout mice have no protein in there. Here's a normal mouse. Here's our treated mice, and this is at 3 days after injection, 10 days, 18 days, 190 days after injection. There's still enzyme detectable in the lysosomes of these animals, see. And so what we think is happening is, why is there enzyme still in the muscle but the glycogen is going up? We think what's happening is that there's sort of, what we're looking at is lysosomal biology and turnover. Here's a muscle cell, here's the lysosomes. We make our enzyme from the liver. It gets into the lysosomes, and it breaks down the glycogen that's in there. So that's how come within a week or two we see the glycogen cleaned out of all the muscles. But then what happens? The antibody comes in and prevents that enzyme from getting into the muscle. Now what happens is that muscle is continuing to get old, and it's making new lysosomes, right? Because it's still going through life. Those new lysosomes start accumulating glycogen. And so as time goes on, even though we've got some lysosomes that are depleted of glycogen, other ones are being formed that have no access to new enzyme, and we see this glycogen slowly rise with time. So there's a couple things. We can take the liver, we can make it force it to produce a lot of enzyme. It can be taken up by a lot of muscles. Once it goes in there, the enzyme actually has a long period of time of ability to clear glycogen, even if it's blocked by antibody. It turns out that this virus, when we injected the first mice, I kind of overdid it, gave too much virus. It worked too well. We can actually dose down, give less virus, and still get ample secretion of this enzyme. So we've got an ability now to do a dosage study. It's not like we have to go full blast, give a high dose of this virus to get this effect. We actually have about a 40-fold, if not better, range of virus doses to see effects in these animals, which is important. If we were going to attempt a human trial, we would want to do a dose increasing study, and we have a range of doses that we think might be effective. See, because the problem here is that this virus, when it goes into the liver, it's going to be toxic at some level. Everything is. And what we have to make sure is that we can come to a point where the virus goes in and does not cause too much damage, but is able to express enough protein that you see an effect. In fact, we can decrease the dose of the virus. This is the highest doses of virus, and as we back down, we can see decreasing amounts of uptake of the virus by various tissues. This is heart. And as you decrease the dose, you can see that the glycogen levels start coming up earlier and quicker. But we still, at several doses, see the glycogen down to 0. This is significantly different from the knockout mice here. And then as you all of a sudden reach a point where the liver is not secreting enough enzyme in that short period of time to correct all the glycogen. So, like I say, liver targeting of this vector can allow GA secretion, and the virus lasts in the liver a long period of time. I'm charged now. Glycogen reduction in these tissues can be, using this method, appears to be sustained in these animals. Remember, these are pure knockout, sort of equivalent to the infantile patient in regards to how much enzyme they produce. The antibody response is limiting the duration of efficacy in this study. And that's why in the patients, I'm conscious of these antibodies because I see what it's doing to our animal studies. Now, I do want to point out that all juvenile and adult onset patients are CRIM positive, as well as a large percentage of the infantile patients. See, our mice are CRIM negative. Remember this business about CRIM yesterday. There's another advantage there, that possibly juvenile and adult onset patients wouldn't make an antibody, and we would even see a greater response than what we're seeing in these mice, which is still not so bad. What are the limitations? This is the cold, hard reality of this that I have to kind of put together in my mind. Theoretically, we can only inject this virus once, see, because once we inject it, that pesky immune response will remember that virus, and when we try and do it again, it'll make an antibody to the virus now, and we won't be able to get it into the liver. Now, that's theoretically a concern, although we're working on this, and we have strategies that we might be able to avoid this. And in fact, the strategies are not that difficult or cumbersome. And Genzyme, I want to make a point that Genzyme had, at first Synpac supported a lot of this research, and now Genzyme is helping us with this research as well. So even though they're putting in efforts into enzyme therapy, they've not neglected this, and they're looking this at helping us look at this as a further option for Pompe patients. What about the human liver? I mean, we're injecting mice. In fact, we did this in quails. We did the same thing in quails. I didn't even know if quails had a liver, you know, or whatever, but we inject the virus into their veins, it goes to their liver, and it does the exact same thing. We get the glycogen reduction, it gets sustained, and that paper is presently submitted for review. But I want to remind you that that's how the enzyme was initially tested before it went to human trial. It was proven to work in quails. So we've done it now in mice and quails, similar to what the enzyme, and shown efficacy. And also, Dr. Barry Byrne in Florida has also done similar studies with a similar vector and duplicated our results. So it's not just me. Other people have also confirmed that this sort of paradigm can work. So that helps sort of solidify it. We don't know, though, is the human liver going to react to the virus the same way these animals? It's just a question that I don't know the answer to, although other individuals are using these viruses, as I showed you, in other clinical trials where they are targeting liver, and we're going to be able to gather that information up and utilize it when we attempt our trial. Can the human liver secrete that enzyme as efficiently as these animals? We're not going to know until we actually do the experiment. And can a dose of the vector be given that is both safe and efficacious, that can work? And that's something that would be an experiment in a human trial. You would have to deduce that. Because of these concerns, you know, when you start thinking about it, how would you want to do this trial if you were going to do it? If you'd want to try and do this in the rapidly progressive form of the disease, which is the infantile or the early juvenile onset forms of Pompe disease, it becomes ethically and scientifically problematic. For example, we go in, we give the virus, we clean out your glycogen, but it only works a short period of time, and then because you have no activity, because you're an infantile patient, you rapidly start reaccumulating glycogen and you're right back where you were. And we have no way of going back in and giving the virus again. See, the enzyme, that's different. You can just keep giving enzyme, and that's why the infantile trial becomes a better trial to test that in. But for this, we have limitations. But how about adult onset patients as a possibility? So I want you to think about this when you go home and consider some of these options. In an adult onset patient, it's not rapidly progressive. Now, I say that, and I don't mean it to be, I see how it is progressive in everybody here, but I'm saying relative to infantile patients, it's not as rapid, and you know that. Although you do see that you do have progression with time. But what's the possibility? Is that we could theoretically inject this vector and clean out your glycogen in your entire body. And then if you're an adult onset patient, you have some enzyme activity. In fact, that enzyme activity got you to be 20 years old, 30 years old, 40 years old before you even had a symptom. Maybe what we can do is clean out the glycogen, and then your residual enzyme will keep your glycogen down for a period of time, maybe another 20 years, until you reaccumulate enough that you start having symptoms. I mean, that's the real hypothesis here, is that what I envision is maybe you coming in, get the virus, clean out the glycogen in your entire body, and then your residual enzyme sort of keeps things under wraps for another, it buys me time until we come up with the next vector that we could either inject you with or something like that. So think about that. And that's what I'm basically summarizing here. You know, like I said, we've got other advantages here too. All your adult patients are CRIM positive. So that means there's a diminished likelihood to make that antibody, which means it may even work better than in the animal studies. We may have decreased toxicity of the virus because we're bringing in a gene that your body is already pretty much expressing and seeing already. The only difference between what we'd be bringing in and what your body expresses is probably one amino acid. And here's the business about patients having GA activity. And so by thinking in these terms, we get rid of the need for re-injection of the virus. We don't have to do it because the biology will capitalize on it. So what do we got to do? Like I said, we've done this in animals. We've done it in several animal models. In fact, we've done, I think, as much as has been done with enzyme before it went to clinical trial. But in my mind, this is different. This is a lot different than enzyme because it's the safety factor is a lot different. This virus goes into liver, we don't know what it's going to do. It's probably going to have a toxic side effect. And so what we have to do is thoroughly define these toxicities in liver models in animals. Okay? So we're going to make a boatload of virus. We're going to inject hundreds of mice at various doses, and we're going to look at that and figure out what exactly it is. What my lab has done is try to design these viruses to make them as safe as possible to try and really boost our chances. And so what I've been struggling with is make the virus as safe as possible and try and design it as good as it can be, because once you make the decision to go ahead, you're committed to at least 6 months to make that virus to a grade that could go into a human, and probably another 6 months before you do all the quality control. You commit a year and a half to that process, and in the middle of that, you don't want to say, oh, I made another one, it's a little better, I think we're going to just drop everything and move on to that. So you're always wrestling with, when's it time? And we're getting close, but we still have to do some work with making this vector a little better and define these toxicities. The other thing we're doing at Duke is we're looking at other ways to deliver that gene into the liver, and we're looking at other viruses that people are using that are potentially safer than the one we've designed. I can tell you right now that this one works the best, and it looks to me like it works the best because it's the only one capable of secreting enough protein to correct all the muscles at once. That's the big objective here. We're even looking at maybe we can inject the virus into muscle instead of liver. Inject it into one muscle and let that muscle secrete the enzyme for all the other muscles in the body to take advantage of. We're looking at that. It actually works. We can see that the muscle can secrete the enzyme and other muscles can take it up, but the absolute amounts are nowhere near what the liver can produce. And I think Nina's got data that sort of supports that. And we're also, and like I said, we're looking at other viruses that are potentially safer for use in liver gene transfer. Dr. Koberl, who you'll probably hear about in a future meeting, is looking at this, and we're seeing how this virus works. So those are the angles, those are the thoughts I want you to think about. Think about if you were approached by somebody who had such a thing that potentially could work on your glycogen. There would be no promises that it would help your muscle strength at all. There would be no promises it would help anything. And in fact, it might expose you to extensive liver damage. Would you want to do such a trial? I mean, that's what I wrestle with and think about. And what I'm trying to do is stack the deck in my favor to make it as safe as possible. But eventually, that's what such a trial would look like. It would be presented to a patient like that. And so I've been trying to sort of tweak people here, think about their opinion to decide when is the right time. And so that's what we're working on. And these are the people in my lab that have pushed forward a lot of this work. N.U. Ding is a postdoctoral doctor in my lab who does a lot of the virus work. Human Hugh, Bradley Hodges, these are all doctors that designed these viruses and injected them and tested them, helped me out. And we have technicians in the lab that produce all this, as well as everybody else in the clinical trial, and especially Dr. Raben and Dr. Plotz at NIH, who supplied us with the animal models, and Dr. Kikuchi with the quail models to test these things and see if they work. And so I'll stop there and answer any questions. Thank you. Yes?
Could you comment on this virus in comparison with the virus that was used in a trial in a teenager in the last year or two where he died as a result of gene therapy?
It's the same. It's the same class of virus. It's an adenovirus, same one. Ours is different. It's safer than that one. I want to comment about that trial because actually, so in my evaluation of that trial, and I've actually looked at the autopsy results on that kid, reviewed what was presented, it's not clear what happened to that child, whether the virus actually was the cause. That child was being treated for a disease called ornithine transcarbamylase deficiency, or OTC. It's a metabolic disorder of liver, so they were trying to get the virus into liver for a liver disease. So the liver already has problems. That's another advantage of considering this in Pompe disease, because generally the liver is not that terribly affected. In that trial, that child's underlying metabolic disease was out of control at the time they injected the virus. In fact, that's why they got slapped with several FDA rules violations, because that child should not have gotten that virus because his disease was out of control, and they violated their own protocol in giving him the virus. I can tell you that other people have received similar doses that he got and have not had that kind of reaction. And in fact, other people have injected this virus intravenously directly into the liver up to as high a dose and repeatedly into cancer patients. For example, in cancer patients, they're giving this virus, and they inject it in the vein, and then they have the cancer patient come back in 2 weeks later and they do it again. They've done it up to 19 times in those patients, and that's published. And the toxicity in those instances is not anything like what was reported there. So unfortunately, the answer is yes, that's the same virus. What happened there, no one knows. Certainly this virus can cause toxicity at high doses, but it has not stopped this virus from being used in well over 3,000 patients, and it continues to be used. And the question is, can we find a dose of this virus that will produce enough enzyme without causing toxicity? That's my opinion now, okay? So others could chime in if they don't agree with that, but I've really looked at that case thoroughly because obviously I've focused a lot of attention on this sort of angle.
Is there any way to make a CRIM-positive mouse model to test whether this would work in a patient that's CRIM-positive?
Yeah, that's we're working with Dr. Raben to look at that. She's actually developed such a model. I'm sure she's going to talk about that a little bit to try and avoid this antibody response. We're actually developing several models. And we're also looking at using those models to test whether muscle can secrete the enzyme just like liver. And in fact, I just got a muscular dystrophy grant to help us look at this as well. So they're also supporting this effort because they see it as a means of not only treating Pompe, but maybe learning about other muscle diseases as well. So I'm gathering support from all arms. Genzyme, Synpac was supporting us, Muscular Dystrophy Association, everybody's. I think, though, with the CRIM positive, it's just going to work better. It has to.
Roy House. Thank you for an excellent report. Is there any other type of gene therapy, like looking at the human genome? Is it chromosome 17 where the problem lies for this disease? And can people manipulate that in some way or another?
I think it's 17. I'm not for sure. But what you're talking about is gene correction. And to physically go in and correct every cell in the body and change that DNA from what it is to the normal, what the normal sequence should be, is not technically possible today. It may be in the future, and there are people looking at different ways to do that. Remember, you'd have to correct most of the muscle cells in your body to do that. So again, that's where the beauty of the biology of this disease, the enzyme does the work. It targets to all the muscle cells for us. We don't have to do that.
If your hypothesis would be correct on the adult form CRIM positive, would one injection be sufficient?
Well, it might be. I mean, the question is, can the adult liver first take up this virus as efficiently as the animal? And then secondly, can that adult liver produce enough enzyme to supply the rest of the body? Then is the form of that enzyme that the liver is making targeted correctly to all the muscle cells? Then once it gets into the muscle cells, is there enough that it actually starts breaking down the glycogen significantly? There's a lot of variables in there. But potentially, if those all come true just like the animals, there's enough there that the glycogen goes down to 0. Then the question becomes, what would you be left with? Would your muscle actually regenerate? Or would it just make your muscle disease stop at that point in time until finally the glycogen starts reaccumulating again? And I will tell you that what Dr. van der Ploeg showed yesterday with the juvenile patient, getting the enzyme and apparently reversing, I'll tell you that's going to change my aggressiveness because in order to propose a trial, I can't, I could not propose that we're going to reverse anything. All I could say is at best we might keep things stable or slow the thing down. But now I can say, and in fact, we might even be able to reverse things, which is something that all this ammunition can be gathered up to justify the trial, not only in a scientist's eyes, but also when I come and talk to a patient, because eventually the patient will have to sign a consent in which you will be informed about all the risks, and likely initially there would be no mention of benefit, period, because we wouldn't be able to guarantee any of that. It would just be risk. But that is the possibility. Certainly, that's what we want to shoot for. But the initial trials would just be evaluating the safety of the virus. And it would be a dose-finding study. Johan.
Andy, you're using the liver to produce a lot of enzyme in the bloodstream. If you were, from the levels of enzyme in the bloodstream, if you were to give that as an exogenous enzyme replacement therapy, what kind of a dose would you have to need to mimic what you're doing in this?
Well, that's a difficult question because, remember, this liver is producing the enzyme constantly. See, when you get the enzyme infused, it's a single bolus injection. The enzyme goes in, and over 3 hours or 6 hours, depending on which enzyme, about 6 hours later, the enzyme slowly goes away because there's no more supply. But the liver is constantly kicking it out. It's 24 hours a day, 7 days a week, either until the enzyme, the antibody kicks in, or until the virus goes away. I can tell you, Johan, that the activity levels that we see in these animals when we spike with recombinant GAA, it's a similar sort of ratio of the activity level to the micrograms and nanograms. And we're getting up around a half a milligram per mil produced by the liver constantly at some of the highest doses. So it's pretty substantial. Pardon?
How much enzyme would that require during the enzyme?
There ain't enough. Yeah. I'll tell you, one mouse makes enough enzyme for itself than a CHO cell factory. One of these cell factories that you make the enzyme. It's incredible. In fact, one of the postdocs in Dr. Chen's lab was like, why don't we inject a cow, make it produce a ton of enzyme, and then pull it out of the cow's blood and then give it to the patients? I mean, theoretically, you could do that. But then you get into all the issues just like other stuff. Here's an animal product that's coming out of an animal and you're injecting. But those are all possibilities. But it's incredibly efficient. But the problem is when the virus goes in, the liver notices it. And so that's why there is toxicity associated with it. Although I don't have data here to show you, but we've minimized that to pretty significant amounts. So you can sort of see where I'm at right now is I'm seeing these results in the animals. I'm seeing we can make the virus better, and it's a matter of just doing some further tweaking and a lot more safety studies that we are close. That I can't keep myself from not seeing you here and thinking maybe it's time.
Then, instead of CHO cells, why don't you produce it in vitro in hepatocytes? If it's a good enzyme, high secretion, as a way of making the enzyme.
So we can do that. We can inject human liver cells in tissue culture, and they will produce the enzyme as well. The problem is it's a one-time shot. So you put the virus in, the way the virus works in the tissue culture is it kills the cells at the time it infects them. Or, see, when you make CHO cells, the cells are being made in big fermenters, and the cells are alive, and they keep dividing and dividing and dividing, constantly secreting enzyme to be kind of sucked off. This won't work for the virus because as the cells divide, they'll lose the virus. You can't keep putting the virus in and in. So, see, because the virus is not stably. CHO cells. Because well, that's a possibility. CHO cells are nice because you can grow them in suspension. It's all worked out how to grow tons of them, and they secrete the enzyme in a form that's phosphorylated, apparently pretty good, that allows uptake. Maybe hepatocytes could, but you'd have to work out how do you grow tons of hepatocytes in fermenters. I don't think that's worked out yet.
Any more questions?
say the toxicity, what sort of toxicity could there be?
Yeah. Well, we're defining that. So what it turns out to be is it could be extreme. It could be what happened in this pen trial. I mean, I could never guarantee that wouldn't happen. What happened there is the child had increased elevations of liver function tests and what's called a decreased platelet count. Platelets sort of prevent bleeding in your body. When you cut yourself and all of a sudden it stops, it's because platelets are sort of plugging it up. Those things are transient, though. See, the virus goes in, you get this transient sort of hepatitis is what it is. It lasts sort of like a flu. You feel bad for a day or so, and then it goes away. And that's what happens in all patients that get this virus, even at high doses. Now, what happened in the Gelsinger tragedy is that he was doing the same thing, and then his ammonia level got out of control, and his ammonia is what's the problem with his underlying disease. And they put him on a ventilator. When they put him on the ventilator, he went into something called adult respiratory distress syndrome. Now, whether it was triggered by the virus or whether it was triggered by the physical act of intubating him or other factors is unclear. That's where it gets cloudy. But it looks to me like the toxicity is a transient hepatitis, a decreased platelet count that goes away within 3 days. But you see, the problem is you could never, the possibility is it could get worse. It could be a substantial hepatitis. And if you don't have a liver, that's not good. You see. So that's why we would do dosing, and we will probably have to do monkeys at high doses just to define this as well, because the safety concerns are much greater than with the enzyme.
I believe it's fairly common for Pompe people to have elevated liver measurements.
They have elevated glycogen in their liver, but as far as function, the liver is essentially normal. That's my understanding. Does anyone?
Does any other Pompe people here get regular?
Are you referring to the fact that some liver enzymes are elevated in the blood? That's probably what you mean. Yes, they are.
Now, which enzymes? Because a lot of those enzymes that you measure actually are from muscle, like AST, ALT. They can be elevated, but they actually are muscle-derived. In fact, many patients go in for, I've seen a couple patients diagnosed with muscle diseases. They got initially referred to the GI clinic because somebody thought they had a liver problem, and then it turned out that they have a muscle problem. But I think it's a fair statement to say that the liver is not the problem in Pompe disease, and the liver is probably pretty normal, which gives us another advantage. We're not targeting an already sick organ.
Any more questions? Perhaps I could just ask the last one then. I'm just wondering, it's a very minor comment, I'm just wondering whether you can tolerize mice, the knockout mice, by injecting your virus soon after birth.
In fact, we can, but there's a problem with neonatal mice. I don't know if you've ever seen a newborn mouse, but they look like they shouldn't have been born yet. I mean, they look like they need to be put back in the oven for a couple more weeks. They're very premature. In fact, their immune system is not on yet. So we can put in whatever we want into a newborn mouse, and it'll never see it as foreign. I could make these results look 100 times better by injecting a newborn mouse, because I know they wouldn't respond to this as foreign. But what I'm trying to do is mimic the situation in the clinic where I'm not sort of stacking the deck.
But you would mimic the situation of your CRIM-positive patients by doing that.
Right. Yeah, you could do that. Although someone could say, well, they're immune deficient completely. That's not what a CRIM-positive patient has. A fully functional immune system. It's just they would not recognize that one protein as foreign.
Correct. I think that was the hypothesis that you used to show that,
Right.
or explain the fact that you had a loss of efficacy.
Yes, yes. See, so Nina has some mice that I think will help me answer this, and we've talked about doing this collaboration. We'll look at this. We also have possibilities of doing this in quail. I don't want to go into, but there's all kinds of angles to answer this, and we will. And rest assured, we're moving as fast as we can.
Well, I think that's a good introduction to Nina to speak next, but thank you very much,
Okay.
Andy, for broadening our horizons.
session. But I'll try to tell you a little bit about what we're doing there. So as you know, we made the knockout mice. And you know probably now what it is. So we literally knocked out the gene, the acid maltase gene, so that these mice are similar to the infantile patients with the disease. They don't make any enzyme. They don't express any, basically it's a gene which is completely non-functional. Now, we're not the only one. In Rotterdam, people had their own mice, and I have to say that those people are never behind in anything. So they had their mice first, the knockout, and basically those two models are very similar biochemically and morphologically. They're very similar. They develop the disease, they accumulate glycogen, they don't have any protein, and both models are what we call immunologically naive. They have never seen the protein, and that's why they develop antibodies when the enzyme is delivered exogenously. There is some difference between these mice, and we never had time to get to it, but we will, hopefully. And the difference is that these mice are clinically, in terms of their symptoms, they are probably somewhat different. So NIH mice developed symptoms before, much earlier, and I think that the symptoms are more severe than in the Dutch model. And we think that it's not because something different was actually done. We targeted what we say, a different part of the gene, but this is not the problem. The difference is a different genetic background, and we now know, the more we know about the mutations, about the individual phenotype, or the way the disease expresses in different patients, even with the same mutation, even in the same families when the genetic background is sort of very similar. We do see those differences, and this is very important because one day we may find a so-called modifying genes, a gene which in one case, in one individual, make the disease a little bit less severe, and in the other one, a little bit more severe. So, but these are the studies which we put aside for now. But certainly the main purpose of making those mice was to test the therapy. There is also another aspect to it. You can study the pathophysiology of the disease, and it's also very important. Like, for example, some of the questions which were raised here, what causes muscle damage? And it's still not clear. Is it that the lysosome which actually engorge and take all the space within the cells, or is it that they break at certain point and release a lot of toxic products which they contain, and those toxic products actually damage muscle cell? It's still not clear. And it's amazing in this stage, and I think that it's more because the genetic studies and all the gene therapy and enzyme therapy studies are so important. The basic biochemical pathways of how glycogen gets into lysosome, how it is degraded by the enzyme, and what actually biochemically happens in skeletal muscle is not exactly clear. This also could be studied in animal models, obviously. But the main purpose, obviously, was to test those therapies. And at that time, it was really coming, the enzyme therapy. So we knew that the enzyme was made in transgenic rabbits. We knew that the enzyme was being made in CHO cells. And, you know, it seemed that the clinical trials, and any trial, was really very feasible. And we thought that these mice would be widely tried for enzyme therapy studies. We offered these mice to any group who studied, who did anything with acid maltase, worked in everywhere. And we sent those mice everywhere around the world. But unfortunately, we could never get the enzyme to test the enzyme on these mice. I have to tell you that, and I'm very happy about it, that it is changing now. It is really, truly changing. It's not just the promise next week, next month, or next year. It is really coming. I have a firm commitment from Genzyme and from Novozyme to try the enzyme at NIH so that we can do these studies. And I emphasize it. It's very important to have an independent result and independent data, because we're not connected with any of the companies. We're clearly not biased. And for us to do these comparative studies, I think it's the best thing. We certainly wouldn't mind so that the same type of studies would be done independently at any other place. But we would want to do it ourselves. Now, you've heard several times, since we didn't have the enzyme, we were not just sitting on those mice, we were doing these studies. And there are a couple of what we think is advances with the work we're doing with these knockouts. And one of them is a generation of a tolerant mouse model. So you've heard many times that those antibodies which develop in the knockout mice and in some of the infantile patients, if you really can say exactly that this patient is cream negative or cream positive, I'm not sure that that's the case. But in fact, you've heard several times that those antibodies very often are to blame for not a very great efficiency of the enzyme. And we actually, at the moment, we still don't know whether it's true or not, whether the not such a great efficacy of the of the gene therapy or enzyme replacement therapy is to be blamed on the antibody. According to some of the studies, that's a direct correlation, and according to the others, it's not. But anyway, we thought that it would be a wonderful idea to generate a mouse model, a knockout mouse model, which would be tolerant to the exogenously administered enzyme. And I'm not going to go into details of it. It was a very sort of a delicate transgenic studies and genetic studies. But we made the knockout mice, which have a little bit of the enzyme only in their liver. This level of enzyme is hardly detectable by all the methods which are available to us. We don't see the protein expressed in the liver, and the only thing we know why liver does contain a little bit of protein, because we do a so-called RT-PCR analysis, which allows to detect a tiny, tiny amount of the expressed protein. So basically, the beauty of these mice is that they're exactly like the knockouts. So their muscle is as affected as in the knockouts. Their heart is affected. Two major organs are in terms of the level of GA activity, in terms of the extent of glycogen accumulation in this tissue, and the morphology. When we look at those PS staining with red staining for glycogen, it's exactly the same as in the knockout. But when we give them the enzyme, and we've done this with the Novozyme preparation of the enzyme, so they do not develop any antibodies. Normally, the knockout mice develop antibody after second, third, and definitely after the fourth injection. So most of the scientists would tell us, you know, those mice are not really very good because we can only do a very short-term studies on them. We can do like 2, 3, or not more than 4 injections into those mice. We've now done 8 and 10 injections in these tolerant mice, and they do not develop any antibodies. We think it's a very important thing because now when the scientists or the companies would want to blame it on the antibodies, would tell them, please go ahead and try it on the ones which do not develop antibodies. And again, we're offering to as many scientists as we could. And one more thing which I wanted to tell you what we're doing with those mice. We basically introduced, in order to treat the disease in those mice, we introduced the gene back into these animals. But we did it in such a way so that we can turn the gene on at different stages of the disease progression. For example, in Andy work with the attempt of gene therapy in experimental animal, we don't know at what stage he introduced the adenovirus gene into it. Maybe it was a very young mice. So basically the question we're asking is, and we will turn this gene on like a switch at different stages, when they are still very young, when we know that the muscle function is still well preserved, then at the later stages when we already see the symptoms, and at a very late stage in mice when the muscle is severely affected, both morphologically and physiologically. And basically, we're addressing a question, is the disease reversible? So can we actually reverse it back to normal, or can we only stabilize it, or it's hopeless after a certain stage? And we've done some extensive studies with that. And the only thing I can tell you, it's all preliminary data now. But what we learned is, and some of the things were quite frustrating, and I wanted to share it with you. The good news was that it was very easy to treat the heart. When you turn the gene on, the heart really gets good dosage of the enzyme, and it treats very well. It's more difficult with muscle. So in fact, we're showing the same thing what the clinicians experience with patients. It's easier to do the heart, and it's much more difficult to do the skeletal muscle. Now, the question which we hope to be able to answer, again, it will be in experiments in mice, but the question we were trying to answer is, how much enzyme is needed into skeletal muscle in order to sustain the disease, or in order to reverse the disease, in order to improve it? And it turns out that our idea is that actually one needs very little enzyme in skeletal muscle in order to remain perfectly normal. Doesn't work in mice, or at least it doesn't work in those experiments. And I think that our idea of one needs very little is based on the fact that heterozygous carriers, we know they have 50% of enzyme activity, and they're perfectly normal. We also know from some of the adult patients, based on their the mutational data, we think that 40% would be quite enough. We even think that 30% maybe, or 25% may be quite enough to remain clinically absolutely normal. But apparently, and these are the data which we get in mice, apparently this is quite true to prevent the disease, but not to treat it, not to reverse it. And basically that's all I can tell you at the moment about this kind of studies, but we think that it will be very helpful for clinicians to have an idea of how much and at what stage is needed to reverse the disease. And one more thing which we're doing with these mice, which maybe not doesn't have an immediate and will not have an immediate usage, but we think that it is important to do. We're trying to disrupt the blood-brain barrier in these mice to deliver the enzyme into the brain of those mice. And we know from the morphology, and now those mice exist for several years, they do develop some brain symptoms. So they accumulate huge amount of glycogen in the brains, and this is actually only related to, it has anything to do with the infantile patients, because we all know that the juveniles and adults do not accumulate glycogen outside skeletal muscle. So we're trying to deliver the protein to the brain, and actually one of the symptoms in mice is seizures. They develop seizures later in life. So we think that potentially it may be eventually useful. And those are the methods we are using for them. These are the methods which have been successfully used in human clinical trials to deliver chemotherapeutic agents to the brain. That's about it.
Thank you, Nina, for a very careful and description of some quite magnificent work. This is now open for discussion and questions.
It has been proven then that in the adult form there is no buildup of glycogen
Yes.
in anything but skeletal muscle?
Yes.
You mentioned that if you bring the enzyme level back to normal, it stops the progress of the disease, which means there'd be no excess glycogen in the cell. How could it work if you increase the enzyme level over and above that, that it could reverse the condition?
Yeah, this is one of the things which we also can do with this system when we turn the gene on at different times. Not only we can turn it on at different times, but we have several what we call lines of animal which express different amount of enzyme, huge amounts, for example. What happens if skeletal muscle expresses 50 times more than normal? Or what happens if it expresses 3 times, 5 times more than normal? And what we actually found is that too much is not good. It becomes toxic. I don't think it's a question which is relevant today, because the problem today with the enzyme, at least with the enzyme replacement therapy, to get enough. Certainly we're not thinking in terms of 50 times more. But for example, for gene therapy, it may be very important. Like if you introduce the gene into skeletal muscle, how much is enough and how much is too much? So we did demonstrate that with a certain level of enzyme in skeletal muscle, it's a very clear toxic effect on skeletal muscle. Now, that's the problem. We basically think about it that we're trying to see how much is needed and how much is enough to reverse the disease. And in our experiments, with significant increase in skeletal muscle, 2 or 3 times more than normal level, we still see some glycogen accumulation.
Right up the back.
Okay, the mice that have the glycogen in the brain, they're infant mice. Is that correct?
Pardon?
The mice that develop the glycogen in the brain, they're infant mice. Infant, small mice.
Yeah, but that's, we have one model. Yeah, they absolutely do not have the enzyme activity.
Okay, are you using that model to also suggest that there may be glycogen forming in an infant human brain also, and that the infant may also have seizures? Is that a suggestion that you're also making?
No, absolutely not, because there is a lot of clinical experience with the infantile patients, and I think that those who treat infantile patients would be in a better position to answer it. But I think that it's known from the literature that there is a buildup of glycogen in the brain of the infantile patients. It doesn't mean that it affects them in any way. I mean, there is no knowledge of the adverse effect of the buildup of glycogen in the brain of infants. But yes, there is an accumulation of glycogen in the brain, and I don't think that anybody disputes it. Is that right?
Yeah, it's right.
It's based on the clinical experience. They are, okay.
It's indeed exactly true what you say, that there is evidence from literature and from the mice that there is accumulation of glycogen in the brain. But now we are treating the infants now for 3 years, and it was a point of concern that they would deteriorate mentally or get seizures, and they didn't, no, so far. But it remains a point of concern.
Thank you, Hans. Up the back.
So basically you're saying it's there in the infants, but it's not at a toxic level, the glycogen.
This is basically, you are now thinking it's a problem of success. Say that those infantile, they were never seen, those infantile patients at the age of 5 or 7, right? So hopefully they'll live up to this time. But nobody had any experience of what happened to the infantile patients if he survives beyond the age of 2. Now it becomes possible. And this is a concern. I'm sure that this is for doctors a concern. That's why I'm saying that ahead of time, if we can try to do something in mice to deliver the protein into the brain and do it safely and efficiently, if this procedure is ever needed, it will be already done in experimental animals. So that is the rationale of doing it. Not because of that we know that it will be needed, but it may be needed, and it's good to, in advance, do the experiments in mice.
Have you reached the point of treating the mice to see any muscle regeneration yet? Are you in the process of that?
We are in the process of that, and so the main thing is that we haven't had a good physiological studies on them, because what we do and what most of the people who presented the data today, they showed you the light microscopy, the PS staining for glycogen, but what's important is we may even clear glycogen in those mice, for example, but physiologically the function of the muscle will probably take some time to restore, and we don't know this. So at this point I cannot give you, and I'd love to do it, but it's a different story. I need someone to do it for me, to study the physiological aspect of muscle regeneration in Pompes.
Maybe one final remark. I don't know about muscle regeneration and how much damage, but definitely you can reverse symptomatology, because this patient in our trial was wheelchair bound for 3 years and he can now run.
It would seem that long range, if you can clear the enzyme, but muscle regeneration is still too slow or not enough for real improvement, that an adjunct therapy of muscle stem cells would be very appropriate. And is there much muscle stem cell work going on that you're aware of?
Not in Pompes. Because, you have to have a priority. You have to focus on something. And I think that since the enzyme replacement, is really here, it makes sense to put all the effort into having the best drug, testing it as quickly as possible, and make it available to everybody.
Okay, thank you very much, Nina. Some wonderful work. Procedures for Pompe. And I guess I want to divide this into several parts. First of all, we want to, in our development of methods for the determination of lysosomal alpha-glucosidase, we have applications for just a diagnostic screen, in other words, to identify Pompe patients from those that present clinically and are therefore at risk for Pompe. Then to look at newborn screening, and you heard yesterday the importance of identifying patients before they have symptoms, and so you can potentially maximise the efficacy and the clinical results from various therapies, and also for monitoring of therapies once they're underway. Now, I just thought I'd locate Adelaide for you. Now, Adelaide is just here, and I guess that's not too far away from where we are at the moment in the US, which is a nice coincidence, and I haven't shifted the images around. But I put this up just to show you that from Sydney across to Perth is about the same distance you have to travel from New York across to LA. So our continents are roughly the same area. I thought I'd just start by going through a process that I like to do when I'm talking about a specific lysosomal storage disorder, just to illustrate that we're really talking about a family of disorders here. And Pompe is part of the lysosomal group, storage group. Now, unfortunately, some of my slide here is cut off, and this is my computer that's doing this. And these are separate points here. So now there are more than 45 different lysosomal storage disorder type, and as I said, Pompe is one of those. But they have common biochemical and clinical properties, and I think if we start to look at the common factors, this is an advantage. Most of the lysosomal storage disorders are pre-symptomatic at birth. They are progressive and often with irreversible pathology, and there's extensive skeletal and or CNS pathology. And importantly, and I've listed this one down here last because I think over the last day we've certainly seen this one. There's vast clinical heterogeneity within each group, and this certainly holds for Pompe. That means, that's a very good question. Thanks, Bob. That means that we have, in the case of Pompe, a range of patients presenting from infantile, soon after birth, to adults, perhaps into their 50th or 60th year. And in fact, what we believe is that there is a gradation of clinical symptoms all the way from very severe infantile to later onset Pompe. Now, I just thought I'd try and explain what a lysosomal storage disorder is in general terms. Here we have a cultured cell from an individual that hasn't got a storage disorder. We've heard all about the DNA in cells, and this is the nucleus where that DNA resides. Then this is what we call the cytoplasm of the cell. If you have a very good look in here, there's a whole lot of membranes and very important processes there to make this cell work. And hidden within all of this is a few lysosomes that make up about less than 1% of that volume that you can see there. However, if you look in a cell here from a patient that has a lysosomal storage disorder, again you'll see the nucleus with the DNA material, and these big holes, like Swiss cheese, are the lysosomes, now expanded out and storing material, in this case that may be glycogen. And so you will see that the order within this very fine machinery in here is disrupted quite extensively by this sort of storage in the lysosome. Now, I just wanted to make the comparison a bit more homely in the sense we have, here's our cell that's not storing in the lysosomes, and we have a lysosome here and over here. But if we make the lysosome like the kitchen in a house where there's reasonable amounts of order and cleanliness after each meal and so on, then this is what some of our kitchens may look like. In the cell, this is what the cell looks like if it cleans up after it has a meal that needs to digest material that needs to be turned over. However, in the case of a lysosomal storage disorder, if you don't take the garbage out after each meal and you just try and store it within the kitchen, this is what happens after a very short time, and you can't work in that kitchen any longer. It's just not possible to do anything in there because of the garbage. Very similar for your lysosomal storage disorder. And I guess what we've been talking about today and yesterday is how to go back to that. And if it's just a matter of taking the garbage out by putting in an enzyme or a gene, then that'd be great. Now, I want to now focus on Pompe, and this is a pie chart of lysosomal storage disorder frequencies or prevalence in Australia, and this is collected over a period of time from 1981 to 96. And in that time, we know that we have all of the lysosomal storage disorders that were diagnosed in our country. And so we can put them on this pie chart. So Gaucher is the major piece of pie here. This represents the commonest lysosomal storage disorder in Australia in this time period here. We go around to here and we find Pompe. And there are some others we talked about yesterday as Fabry's under under clinical trial, and there's several other on here that are also under clinical trial for enzyme replacement therapy. Now, we know that Pompe is an autosomal recessive disorder. We heard about that yesterday. The deficiency is this lysosomal alpha-glucosidase, and we have storage of glycogen and glycogen fragments in those garbage bags or lysosomes. And I just wanted to emphasize this point again, that the clinical presentation is within a continuous spectrum from infantile to adult. And that may be a bit controversial in the sense that we like to divide our patients into infantile, juvenile and adult onset, but I think the evidence out there really is that we have a continuum. Now, the diagnosis of Pompe up until now is based on enzymology in muscle or skin fibroblasts. The muscle biopsy is taken and is assayed for glycogen and also for the presence and absence of that lysosomal alpha-glucosidase. Or there could be skin fibroblasts taken, and these are grown out in culture and can be analysed for the presence of that enzyme or absence of that enzyme. These are invasive procedures, and they take many months, often years, to get a diagnosis, because it's often the last thing that a clinician may wish to submit their patient to. Now, the incidence in Australia, this comes back to the pie graph, but it gives you some numbers. In Australia, it's about 1 in 200,000 births we have diagnosed a Pompe patient. In the US and Netherlands, based on carrier frequency, it's about 1 in 40,000. We believe that there's probably a lot of Pompe patients out there that remain undiagnosed, and the incidence could be somewhere between 1 in 40,000 and 1 in 200,000. So we would need to have better diagnostic methods established. And of course, we've heard about therapy and the importance of enzyme replacement therapy. We have clinical trials, and we heard Andy talk about gene replacement therapy. Now, I'll come back to what I wanted to talk about this morning. We want to establish the methodology for our diagnostic screen, and then I'll speak very briefly about newborn screening, and I'll just mention this again. The technology that we're developing can be used to monitor therapy. Now, some of you may recognize this. You'll have a different size card or shaped card with different information on it. This used to be known as a Guthrie card for screening of newborns for, say, phenylketonuria, galactosemia, or hypothyroidism. And in your country, I'm sure most states will use a card with a drop of blood from a heel prick from a newborn baby. And what we do is to punch out, this is a 3 millimeter punch from this blood spot here. And on this particular spot, we can do all of our assays that I'm about to describe to you. Now, this is a bit complicated, and it's got two parts to it. And if we look at, this is what we want to do. We want to measure this particular protein, the lysosomal alpha-glucosidase, that's present in the lysosome. And we have two methods. And the first method is shown here in this half of the slide. And this is, if you like, a plastic sheet or a bottom in a well, and I'll show you what this particular device looks like in the next slide. But what we do is attach polyclonal antibodies that recognize the alpha-glucosidase to the bottom of this plastic dish, and then we put in the extract that we get from that 3 millimeter blood spot, and anything that is alpha-glucosidase will bind to this antibody. We heard about the use of antibodies or the hindrance of antibodies in enzyme replacement therapy. Well, this is where they can be used to actually capture a specific protein that we're interested in assaying, and this is the alpha-glucosidase. So this is these green oval-shaped blobs. And then we have another antibody that's called a monoclonal antibody that recognizes a specific part of this alpha-glucosidase, and we have labeled this with a compound called europium. Now this fluoresces, gives a highly fluorescent reaction, and when we put it under certain conditions, and so we can identify in this what we call sandwich assay, where we have here the polyclonal antibody on the bottom that's from the serum of a rabbit that's been injected with the alpha-glucosidase to generate the antibodies. We then get the alpha-glucosidase to bind to the polyclonal antibody. Then we come in with this very sensitively labeled monoclonal antibody that finds all of the alpha-glucosidase that's bound in this well. Then we can use a special fluorescence measurement to quantitate how much of these green blobs we have in the well. Now, why have this slide up? The next part here, we also use a polyclonal antibody attached to the plastic dish or well. This captures the alpha-glucosidase, but instead of using the monoclonal antibody that's got the fluorescent tag on it, we come in with what we call a substrate. It's just like glycogen, except it's an artificial glycogen, where we're going to measure the ability of the enzyme to break those two glucose sugars that come together, alpha-linked to form glycogen. This is where we have the glucose is linked to a fluorogenic compound that when it's broken away from the glucose, fluoresces. So it goes from a non-fluorescing reagent to a fluorescing reagent when the enzyme acts. And so you can now measure here, this is measuring how much protein is in your sample that is due to the alpha-glucosidase itself. So that's a protein measurement. And we heard several speakers yesterday talk about the protein. And we also had several speakers talk about the activity of the alpha-glucosidase and how that's important to have present in your preparation. So here we have a combination. This assay tells us how much alpha-glucosidase protein is in that 3 millimetre blood spot. And this assay, a separate one, tells you how much alpha-glucosidase activity is present in that same blood spot sample. Now, I thought I had a slide that would just show this particular component here. You see the size of the hand here? This is what we call a 96 well plate. So each one of these dots you can see is a separate well, and in those separate wells go one 3 millimetre blood spot. And so you can theoretically carry out 96 assays in that plate there. And all of this can be automated. Both the loading of the 3 millimetre blood spot and the processes of putting all the reagents and washing and then measuring the fluorescence, all of this can be done in a machine without human interference. And so you end up with a lot of data. Now, what we did to evaluate this particular technology was to use these particular samples. We had 96 newborn control blood spot samples from the Guthrie cards I showed you. We had 215 adult control blood spot samples also on those cards. We had cards that Pompe patients donated blood to, and we had 2 infantile, 3 juvenile, and 12 adult. And we had 3 Pompe carriers donate some blood to us for this assay. Now, it's a little bit complicated, but here we have, this is determining the amount of alpha-glucosidase protein present in the blood spot, the 3 millimetre blood spot. And so here we have some numbers up the side which just give you the units of micrograms of alpha-glucosidase per litre of blood on that spot. And this is our newborn blood spot samples. You see they range from here, which is about 25, up to about 155. And there's what we call an outlier up here. So this is the range of values we get in the newborn population. Then we look in the adults. These were collected from the Australian Red Cross donor samples. And you can see the range is lower than what we see for newborns, but the average is lower than what we see for newborns, but we have a similar range, if you like, of values, from something's about a little under 10 to something's about 60. And then we look at Pompe. All of the 17 patients are treated the same here. We have We have most of them below the lowest level that we see in the control samples. We have some outliers here where there's protein present in the Pompe patients. And these are the 3 heterozygotes you see, and these are adults, and they're about half normal, which is what you would expect. Now this is what happens when we measure the alpha-glucosidase activity, and that's that second box that I showed you where you're measuring the ability of the enzyme that's in that 3 millimeter blood spot to specifically cleave that fluorogenic substrate, because you've only captured the acid or the lysosomal alpha-glucosidase. Now you see, again, we have the spread of data, and all of the samples from the controls are above the 0 point, the non-detected point. When we get to the 7 Pompe patients, they're all non-detected with this particular method. And the heterozygotes, again, are about half normal. Carriers. Sorry, I launch into words I shouldn't use. Now, this is just detail, and perhaps some of the people in the audience that would like to see the hard data would appreciate this. This is plotting the activity in the newborn population. This is the alpha-glucosidase activity against the alpha-glucosidase protein. And you get this nice relationship here, which you would expect if you're measuring protein and activity in the same molecule. And if we do in the adults, you can see the spread of data, and that's consistent with what we saw on those box plots that I showed you. But again, there's a linear relationship between activity and protein, but that gives you an idea of the spread of data. Now, just coming back to these blood spots, I think these are very easy to collect from anybody. We collect it from a heel prick from a newborn, and that's done very efficiently by people who know how to do it. But for adults or children, it's very easy to just take a finger prick so that you have some drops of blood that will fall onto the blotting paper. Now, I wanted to just extend this talk to go into what we've done for newborn screening. And I'll just put this up. These are the 2 methods that I talked about. And I want to show you what happens if you apply these sorts of methods now to screen nearly 2,000 newborns, just to get some idea of the numbers. And what I've got here, it may look a bit confusing, but what we've done is that we've looked at, this is the alpha-glucosidase here in protein across the bottom. And up here is the frequency. In other words, in this particular block of individuals that show a value between about 33 and 40, they average 300 in the population of 1,951 that was screened. This is all done automatically. And this insert here, we're really looking down in here for low protein as an indicator of Pompe disease. And this is an expanded view of this particular area here. And if we put on the Pompe patients, here you'll see 13 are down in this region. 2 of the Pompe patients are here, and there's 1 up in here. Now, this what we call 1% of the total population, this is from here to here. The patients or the individuals that fall from here to here represent 1% of those 1,900 patients that were screened. And with a combination of this particular assay for protein and activity, alpha-glucosidase activity, it should be possible to diagnose patients within this particular newborn screening method. Now, there's one other thing I want to tell you about, and that's looking for glycogen and glycogen fragments in these sort of samples. This is what we call a tandem mass spectrometer. So this one here, and this machine, and the component parts, extremely valuable and sensitive in its ability to measure very low levels of glycogen fragments. And this is what we call a trace from one of these machines. It's all done automatically, and we can spit out the data and plot it up. But here, I just want you to look at, this is a pattern we get from a normal individual or a non-infected individual with Pompe or without Pompe. And here is a Pompe patient here. And I just want you to look at what we call glucose 3, glucose 2, and glucose 4, and glucose 5. What this means is that for glucose 2, there are 2 glucose molecules that are bound together by what we believe is an alpha linkage. And there are 3 glucose molecules bound together here in a chain, 4 glucose molecules in a chain, and 5. They're all elevated in this sample from the Pompe patient. And we see that in all or most of the patients. And this just shows you that in this, again, a box plot where we have, we're measuring the disaccharide or the 2 glucose, 3 glucose, 4, and 5. And the red represent the control infant values, and the green represent the values that we get from the Pompe infants. And you'll see that the green is elevated in all of the what we call oligosaccharides of glucose from the Pompe patient compared to the unaffected controls. Now, well, I'd just like to summarize at this stage, we've developed an immune quantification method that enables us to measure the amount of alpha-glucosidase protein, that's the lysosomal alpha-glucoside protein, and its activity. And we have developed methods that with exquisite sensitivity and specificity based on antibodies, selection by the antibodies that recognize these particular molecules as very special and specific ones. We've developed a non-invasive, cost-effective test for Pompe disease, and we can do this off a 3 millimeter blood spot. And of course, we believe we have applications for this technology in our diagnostic screen, the newborn screening procedure, and certainly to monitor therapy. And of course, all of this work can't be done without input from a lot of people. Again, I've lost my arrows here off the side. The South Australian Newborn Screening Centre, the Australian Red Cross, who kindly gave us access to de-identified samples. The National Referral Laboratory, these 2 lines here fit together. That particular service does all of the lysosomal storage disorder testing in Australia and the Asian Pacific region. We had assistance with antibodies from Erasmus University. We had assistance from a number of referring clinicians around the world who sent us samples, and these are very, very valuable to us. TLH Research, which from here, Farming, and the National Health and Medical Research Council of Australia, who have supported our work for many years to develop tests and therapies. And I just wanted to show you some faces here. Peter Meikle has been involved with the development of a lot of this technology, and much of this is his work. Enzo Ranieri, who is in charge of the newborn screening program in our hospital that carries out the service for 2 states and 1 territory in Australia. And this is the group. We need another photograph because it was taken in 1998. But this is the Lysosomal Diseases Research Group in Adelaide, in the parkland outside the hospital. And that's a friend from Kangaroo Island, just off South Australia. And I thank you very much for your attention. Now, are there questions or comments?
Why 3 spots? I have to say, in Dr. Hopwood's lab, a lot of samples were analyzed from the mice, and I always have problem delivering you those 3 spots.
Right.
So it turns out that you don't need them. 1 would be enough, isn't it?
Oh yes. Definitely. I've exposed myself as being greedy, and I'm sorry. Actually, our standard cards now are going up to 5 spots, because in South Australia we're currently screening for 38 different genetic disorders, and they're proving to be very valuable from the point of view of early detection and prevention programs that we have going in Australia. So that was an old card, and I probably sent you an old card, but the newer cards have 5 spots. So if I send you a new card, just send me 2 spots with blood. Right up the back.
Jose's got a question. I can ask. It says on the internet, I've seen different names describing the same condition. Why is that? And don't you think it creates confusion?
I guess this is Pompe versus acid maltase deficiency. Is that?
Yeah.
Yeah.
I've seen other names also. Describing Pompe.
Yeah. Yes, I think, perhaps there is a time when we all of the people in control of textbooks and policy and nomenclature should agree to call it one particular disorder. I would prefer to call it alpha-glucosidase deficiency. And just to complicate it a bit more than that, I guess it has to be acid or lysosomal alpha-glucosidase deficiency. And I'm sure that there would be a considerable debate about what we should call this particular condition. But I agree, it is confusing, and I guess people like myself should be very careful to put up a list of what these conditions are known by, so that you can recognize one that may be familiar. Thank you.
I was just wondering if, is this screening available in the United States yet, or is it just in Australia?
No, this is just a glint in a researcher's eye at this stage. What we want to do is to develop this further, to introduce newborn screening for all lysosomal storage disorders, to actually screen for Pompe, which has an incidence of 1 in 200,000, is considered not to be commercially or economically feasible. To pick up 1 patient in 200,000 births would be very expensive. So what we have been doing over the last 5 to 10 years is working up methodology that will enable us to screen for all or most lysosomal storage disorders in one set of assays from those Guthrie cards. And we're in a sort of a validation clinical trial, further optimization of this data at the moment in Australia. And when we have satisfied ourselves that we can do this, then it's up to the various screening laboratories around the world to decide whether they want to take that on board as a standard screening test. But you would appreciate that there are a number of examples, and we heard yesterday about the importance of picking up Pompe patients as early as possible and beginning a therapy that's efficacious to gain the maximum from the therapy. It's the same for many other lysosomal storage disorders. That's something that Pompe shares with many other disorders. So to me, newborn screening is a very important thing to introduce eventually.
How common is phenylketonuria? Is it more common than the lysosomal diseases?
The question was, is phenylketonuria more common than the lysosomal storage disorders? Yes, it is more common than any one lysosomal storage disorder. In our country, and I think in the United States, it's about 1 in 15,000 births for a PKU. And of course, there's effective therapy once that PKU patient or individual is identified with modification of diet. With lysosomal storage disorders, we believe the overall incidence of lysosomal storage disorders in our country is about 1 in 5,000. Now, that means that if we had a common method for screening to pick up most lysosomal storage disorders, we'd have an effective program to identify patients where we can apply therapy and prevent the development of symptoms. And in our country, we also screen for cystic fibrosis, and that has a prevalence of 1 in 2,500. So if you look at the lysosomal storage disorder group, which Pompe is part of, then certainly 1 in 5,000 is quite a reasonable group of disorders to screen for. It's a matter of developing the technology to enable that. Right up back.
You had a couple of symptomatic Pompe's outriders that were not picked up. You drilled down to see why they weren't?
On that, yeah, they were adult patients where that screen result of newborn screening that I showed you with the 1,951 screen, when we laid those Pompe patients onto that, that was for protein. But if you went back and measured activity, you would discriminate those patients again away from the normal controls within that cohort. So that's the difference.
So those outriders were adults?
Yes. Yeah. Yes, right up the back.
Is
Please,
there a
sir.
different analysis to determine a carrier versus a victim?
I've cheated a bit by only showing you 3 carriers. That's all we had. Being a statistical person, I would suspect that if we did enough of these carriers, we'd get an overlap between what we call the normal range and the carrier range. And this is what we find with a lot of lysosomal storage disorders for what we call autosomal recessive conditions. And it's not surprising because of the variation we see in activities and protein expression for lysosomal proteins. And I guess what I'm coming around to conclude is the best thing to do if you want to pick up a carrier is to look for mutations and follow it by mutation analysis rather than protein or activity measurements, although you will get some idea, but I think you have much greater certainty if you look and use mutations. Bob, could you use the microphone?
Was I correct in observing from your figures there that carriers also have decreased protein and enzyme activity?
Correct.
But they don't have symptoms?
Oh, that's fine. That means if I want, perhaps I can talk in a little bit of enzymology lingo here, and what that means is that if you look at for the amount of protein that a carrier has got versus the amount of activity, that ratio is exactly the same as you see in the normal population. That's what we call a specific activity. And so they have normal protein that's being expressed. It's just as active and functioning as the protein we see in non-carriers. That's the rub. Sure, the total protein, alpha-glucosidase protein, and total alpha-glucosidase activity is down by about half, but they're both down by about half, and this means that you've got normal enzyme in there with normal activity, but it's only half present, half of the amount present compared to the normals. And we had a discussion this morning, how much enzyme do you need to prevent symptoms from developing? And we know the carriers are symptom-free, and I guess there are some other examples where the numbers are quite much lower than 50%, and so we could guess maybe 20%, maybe 30%. This is all guesswork. In some other lysosomal storage disorders, we know that 5% is enough, but it does vary from one disorder to the next, enough to prevent symptoms. Go right up the back, with the hat on.
I'm just kind of curious as to why
glycogen doesn't seem to have any effect on the nucleus of the cell. It seems to be, it doesn't seem to go there. Just slightly.
Well, I mean, I think there's some experts in the room that may be able to tell you about the how glycogen gets into the lysosome, but certainly glycogen has no known pathway or track to go to the nucleus. That's a separate part of the cell. It hasn't got the sort of the networking or the trafficking of glycogen or pathways that would take glycogen into the nucleus or any need for that. But there is a process of getting glycogen that's required by the cell to function and to create energy from breaking down the glycogen into glucose, that somehow or another the glycogen is encouraged to go into the lysosome. So that's a specific pathway. Just like Andy was talking about these targets on the alpha-glucosidase protein to get the enzyme into the lysosome by what we call a receptor-mediated process. These are these phosphated mannose residues. They bind to the receptor on the cell surface. That internalizes the enzyme and takes it to the lysosome. I don't know what the mechanism is of getting glycogen into the lysosome, but presumably it's quite specific. And there's no mechanism that is known or need for to have glycogen in the nucleus.
Yeah, I have a three-point question. The first has to do with the cost-benefit ratio. I'd be curious as to what it costs to do one test. Be curious about your methodology for the total 38. I'm assuming you're using more than just mass spectrometer if you do 38. And you said with lysosomal disorders you got down to an incidence of detection of 1 to 5,000. I'm assuming when you look at the total 38, it's even less than that. Then I want to, that's one part, is cost-benefit ratio and exactly what you charge for one test. Secondly is a question about input, and thirdly, a question about output. When you're making a recommendation for an entire population base, it requires a lot of different types of people, technicians, nurses, clerics, etc. How often is the specimen mislabeled, or how often does the specimen not even get to you? And then with respect to output, how long does it take for the report to get back to a physician when it is positive, or how often does it not even get back or get to the patient?
Okay. Thank you. That's quite an intense list there. What I've done, I think, is I've introduced newborn screening, and that's a very emotive but very important topic to discuss in our community. Now, if I could start dealing with the cost-benefit ratio first. In Australia, or certainly in Adelaide, where we screen for 2 states, we charge for those 38 conditions that we're screening for, we charge $12.50 Australian. Now, last time I looked, you could get 2 Australian dollars to the American dollar. In other words, if you like to put the $12.50 into American dollars and cents, it would be $6.25. Now that's a pretty good return for the sort of number of tests that we do, because it certainly is extremely cost-benefit. If we find one affected patient a year by that methodology, we've more than saved the cost of carrying out the test. In fact, in the screening population that we screen for, there's more than 30,000 screened in that one laboratory. And we would expect to find 2 PKUs, the order of, about 10 to 12 cystic fibrosis patients. We'd find a number of MCADs. All of these are going to benefit enormously from that investment of $12.50 by 30,000 in just finding one that you can save the life of or prevent from being institutionalized. So and there's no doubt about it, these days there is enormous cost-benefit gains from newborn screening where there is effective therapy, and it comes down to that. Now, does that cover some of the issues? I think you were after some other points and they've gone right up.
I was just curious about your system of check and balances.
Oh, yes.
Obviously, there are going to be errors and mistakes made with so many people involved in this process.
Yes. If you go and look in a newborn screening laboratory, certainly in ours, there are a very selected group of people that are involved in newborn screening. We do have we have laboratory technicians, we have the clerks, we have medical geneticists, we have medical genetic counsellors. We have a vast array of people involved in this. But we have a very good accounting system for the samples. And over the last, we did an audit just recently, over the last 5 years, we've only lost 2 spots. And that wasn't due to the papers going missing, because they're all barcoded and very carefully collected by people that we don't rely on their families to post the spots in. They're collected by nursing staff. And there is a very good accounting process of what time that was collected, where it was sent, at what time, and then it's cross-checked that it is received in a laboratory. And so the 2 that didn't turn up in that period of time, we found that some patients are discharged from hospital after giving birth within a few hours. It's quite a remarkable process of change in the last 10 or 15 years. And one of the reasons we've developed mass spectrometry for PKU determination is that the old Guthrie method required the blood spot to be collected at least 3 days, maybe 4 days after birth. If you collect it sooner, then the old Guthrie method didn't work very well. And so now with mass spectrometry, you can collect a few hours after birth, if you so wish, and you'll get a result that is diagnostic for PKU. So the 2 that we didn't collect, they just went missing. We have a population where sometimes people just go what we call walkabout, and you can never find them again. And so it's all right to have a district nurse to go out and look for these people, but in the end she can't. If she can't find them, they're gone, and we know that the baby's been born in an institutional hospital, but haven't been screened for. So out of that, maybe 90,000 over 3 years, we've missed 2. It's not a bad return.
Getting the report back to the physician and the patient in a timely fashion when it's positive, how do you know it gets to the patient?
Well, again, there's a well-orchestrated process. If there's a straight diagnosis, say for PKU, then that's transmitted back to the referring physician, whose name and contact details appear on the card, and then there's a process of counselling. The family will come in and is counselling by highly trained genetic counsellors, and then the therapy would be instituted immediately. And then there's monitoring of that therapy over the years to make sure that whatever therapy is being applied is maintained. Is that okay, good. And any further questions? Yes?
There's a notable difference between the incidence in Australia and the United States. Are there any prevailing theories as to why the difference?
The question was, there's a notable difference between the incidence of Pompe, in Australia versus the United States. I can only tell you what the numbers are from straight referral of patients to our laboratory, and it's 1 in 200,000 over that period of time, 16 years. And the values that I showed for the Netherlands and the US, I believe, are not based on patients diagnosed, but what they did was measure 2 common mutations that are in the adult population of Pompe in a random collection of blood from many individuals in the community, and they found what we call is the carrier frequency of those mutations in the community. And from that, if you use a little bit of mathematics or arithmetic, you can work out how many affected individuals there should be in the community. If you carry out that calculation, then you get a number of 1 in 40,000. Now, there are all sorts of explanations of why the numbers are therefore different, and one I offered was that we're underdiagnosing the patients in Australia because of the methods that have previously been used, or perhaps those figures that were used to calculate the carrier frequency, there's some error in the way that it's been done. I don't think that's the case. I rather suspect that we miss Pompe patients, particularly late onset ones, because the diagnostic procedures are not adequate or too difficult to contemplate for patients and referring clinicians. Arnold, would you like to comment on the frequency story?
Indeed, the 1 in 40,000 was a calculation, but then also we counted the number of referrals over the past 20 years in the Netherlands, and we came to the same figure. So for the Netherlands, these figures are solid, and I don't know for the other countries.
Does anyone know for the United States?
Did you in your survey contact the Glycogen storage disease laboratories in Australia and also about this disease?
As far as we're aware, Johan, we're and a lab in Brisbane are the only laboratories diagnosing Pompe. There's a group in Melbourne that were diagnosing glycogen storage disorders. They're now out of business, but we are aware of all of their cases. They always send on any cases that are likely to be the Pompe to us for diagnosis. So there were no, as far as I'm aware, no Pompe patients within the glycogen storage disorder group in Melbourne. And that's the only other place that we're aware of. Okay. How are we going for time? Okay. Perhaps I could introduce the last speaker, Kevin O'Donnell from the UK, who's going to tell us about the international movement for the Pompe.
I'll soon take care of that. You'll be nodding off. This represents a bit of a promotion for me, because the other times I've spoken at an AMDA conference, an IPA conference, I was actually, Marlon House's warm-up act, basically, and Marlon came after. But I've been allowed to sort of go off on my own. But I think the idea is I'll generate some discussion, and and we'll all take part in that afterwards. Okay. Yeah. Why patient groups matter. This is the sort of things I'm going to talk about. My family story, because my whole attitude to patient groups and why I think they're a good thing is obviously bound up with my own experience. It's important to understand that. The role of patient groups, I'm going to spend quite a bit of time talking about the role of patient groups. Bound in with that is the internet and GSD net, with which some of you will be familiar, I think. And then the International Pompe Association, which is sort of the latest development on the scene. Now, very important, you'll see in the program, sure, very important, you'll see that in the program I'm described as Kevin O'Donnell, Ph.D. Well, I'm not speaking as a scientist. This slide is here to remind me that I'm speaking as a dad, so bear that in mind. Yeah? Okay, is that better? Yes. Yeah? Excellent. Now, one important point I'd like you to remember is I don't know half as much about Pompe's disease as I think I do. Now that's a sort of health world that should be attached to everything I say. Tell you that for two reasons. One is so that you can bear that in mind if I stray into sort of medical or scientific territory that I'm not really qualified to speak on. And the other one is that at some point, somebody's bound to say to you, oh, Kevin O'Donnell, he doesn't know half as much about Pompe as he thinks he does. So now you'll all be able to say, yeah, no, he told me so himself in San Antonio. Right. So my stories as a dad, and it really revolved. This is our first child, Callum. My story starts back in 1993. In 1993, June 93, life was great. I'd just got my dream job, head of my own molecular biology laboratory in Edinburgh, which was a city I'd always wanted to live in. We'd been living in a place called Slough. You don't need to know where Slough was. You just need to know the sound, okay? We'd been living in Slough. Now we're moving up to Edinburgh. We just had our first child, and I had the world at my feet. And within a few months, that had turned to dust, because Callum, this photograph is actually quite deceptive in some ways. The day after this photograph was taken, we got the diagnosis of Pompe's disease. And although you can see it looks as though he's sitting up here, there's actually somebody at the side holding his hand to make sure he stayed upright. He was never able to sit upright for any great length of time. And, I guess if we'd known he had Pompe's disease, we wouldn't have been trying to make him sit upright. And he's smiling here, which is nice. It's a nice way to remember him. But I think there's actually another photograph in this set which is taken maybe just before or just after. And you'd be able to see in that he has the characteristic Pompe's mouth. He's smiling here, which maybe disguises that a bit. So we got this the day after this photograph was taken. We got this diagnosis of Pompe's disease, which we'd never heard of. As I guess none of you had either until you came across it in that personal way. The situation we were in, they couldn't tell us anything about Pompe's disease. They couldn't really give us a coherent description of it. They couldn't really answer our questions about it. They certainly couldn't tell us anything about research. All we were told was essentially, your son has this disease. We don't know about any treatments. We don't know about any treatments on the horizon. Don't know about any research. Don't know very much about it, in fact. But we do know that he is going to die from it. So that was our story. That shapes my perception of what patient groups should be doing, because that's a total absence of any useful information, of any contact with anybody else, was a gap that I wanted to help fill. So that's what shaped us. And of course, needless to say, there was no happy ending here for us. Callum went into a very steep decline. He had a very enlarged heart, and that affected his lung function quite dramatically. And in fact, he died 2 weeks later. This is the last photograph we have of him. So not a happy ending for me. But that's as sad as this talk gets. It picks up from here on. And one thing I wanted to share with you was that although that story has not had a happy ending for us, we did have another happy beginning. 2 of them, in fact. And this is my son Ewan, my daughter Katrina, who were born after Callum, and they were both fine. In fact, they had a... Is this going to work? I don't think it's going to work. Oh, too bad. That was supposed to be a wee bit of video there, but it hasn't come off. Never mind. Okay. What do patient groups do? Inform. This is the key thing. The first thing I did was I wanted to get down and go to the medical library in Edinburgh to try and find out more about this condition. I did so, immerse myself in all these journals, these sort of big dusty rows of medical and scientific journals that hadn't been disturbed for quite some time. And I found out that there was work going on. There was some remarkable work going on in Rotterdam. And I know that Arnold and Anne always get a bit embarrassed when I go on about this work, but it was amazing for me to find out that, contrary to what I'd been told, there was actually some very, very good research going on in this laboratory that, to my mind, as a layperson looking at it, an informed layperson looking at it, clearly had the basis for a treatment in future. Now, that was a story that I wanted to tell other people, and that was one of the reasons I got involved in the patient group. I'm down as from the Association for Glycogen Storage Disease in the UK. That was an existing group, as there was an Association for Glycogen Storage Disease in the UK. But the problem we had, of course, was that these groups tend to be dominated by glycogen storage disease type 1. There isn't really the kind of emphasis on type 2. But rather than set up a new group, because the UK is quite a small place, we set up our own section within the AGSD-UK, and that's the way we've progressed. So I wanted to tell people about this work, and the AGSD published something which had the snappy title of Recent Advances in Research into Pompe's Disease. Great title. I've since renamed it Pompe's Disease, A Guide for Families. I think some of you have probably seen it. The other thing I did, and this only occurred to me the other night actually, what an important thing this was. You know, when you lose a child, you're a freak. You are a freak. You've had an experience that is outside of the usual range of experiences that people have, or that they even want to imagine. Something bad has happened to you. People don't know how to deal with you. People don't know what to say. People are embarrassed or whatever. They've got some maybe fear in the back of their mind that it's going to happen to them. And you find out who your friends are, because people will actually cross the street to avoid you. I hope that's something that none of you ever have to find out, but take my word for it, it happens. So imagine then, there's this guy who's just had a child who's died, and I call up this guy, Arnold Reusser, and say, you've never heard of me, but I don't have any money to offer you, I've got nothing to give you, but I want you to tell me more about your work. And I think it would have been quite an understandable reaction to say, well, I'm a busy guy, you know, thanks but no thanks, I don't have any time. But he didn't say that, he said, let's go out for a beer. It's a very, very, very Arnold sort of reaction. And that really gave me the encouragement to keep on with this kind of stuff. Okay, so that's information. Information, very important. And that's something that Rando and Marlin have carried on. In fact, Rando and Marlin have, rather than just producing information, newsletters or pamphlets or whatever, they've been proactive. They've actually got scientists together. Okay, the scientific conference that was to be twinned with this one had to be cancelled. But it's one of the great unsung achievements of Rando and Marlin House that they've organised the two biggest Pompe's conferences in the world prior to this one, scientific conferences, and got people together in the same room for the first time. You know, an incredible achievement. Not many people are maybe as aware of it as they should be, so I'm happy to acknowledge that now. Oh. Back. Okay, the other thing we do is we support. Support. Right? It's a very isolating experience having a rare disease like Pompe's disease. You know, I'm sure you've all been in the position of feeling you were the only patient in the world or the only parent in the world or whatever. I mean, look around you. You're not. I mean, what a boost it is just to be with people who understand about this condition. And you don't have to go into a long explanation to explain why you are the way you are or why they have the problems that you have. And just to be able to share that with other people is an incredibly strengthening thing, I think. So support, patient group support, very important. Campaign. The AMDA is a good example of campaigning. I think the proactive way that Rando and Marlin have gone and knocked on doors and made things happen and, you know, dragged people along by the scruff of their necks. There's a lot of things that would never have happened if it hadn't been for the campaigning role of the AMDA in particular. Very important. And empowerment. Empowerment. The fact that you've been here at this conference, I think, empowers every one of you. Okay? Because you now know more about Pompe's disease, more about what's happening in Pompe's disease than most medical professionals in the world. They certainly haven't seen the results of the juvenile trial from Rotterdam because it hasn't been published yet. So you have informed yourself, you've become, to a certain extent, your own experts. Not to the extent where you could replace medical advice, but you're no longer reliant on others for information. You have your own information. So that's individual empowerment. The other thing is that it's when you gather together, you can do more things than you can do individually. And there's a number of things that I think we need to gather together in groups to counteract. Okay? One is we need to gather together to be a strong group to represent ourselves against the companies. Right? And I think we've seen that in the run-up to this conference. The companies don't always act in our interest. And it's not because they're bad people. Far from it. You know, John Crowley's one of the finest men I've ever met. No doubt about that at all. But it isn't enough. It isn't enough. It certainly